All right, welcome back to the EECS 370 discussions. This week we're doing a bunch of Project One related things. So the conceptual basis behind Project One, which covers the entire LC2K ISA, and then a couple of implementation things that we can look at today. So let's get started. This is the Winter 22 semester. So if you're watching this in Winter 22, these are the things that are upcoming. Homework 1 today, and Project 1A due in 3 days. So this semester, all the homeworks will be due on Mondays or Tuesdays, and all the projects will be due on Thursdays. So the next couple of weeks, we're going to have some sort of project thing due every Thursday. So make sure to stay on top of that. But for now, Project 1A is the thing to focus on. And I think combined, Project 1S and M would take longer than 1A. So if you haven't started that, now's the time to do it. Right. So our goal today is to look at the conceptual basis for an ISA. So ISA, that stands for Instruction Set Architecture. And so we have this ISA called LC2K that we've created specifically for this class. It was created, I think, 4 decades ago, around 1980, specifically for EECS 370. And it allows us to take a really basic example and generalize it to all the major steps of building an ISA in just 1 semester. And so Project 1 is going to break that into 3 parts. First, actually getting what we would call code into machine readable code, then running that code like an actual program, and then actually being able to write programs for this ISA. And so that's going to be Project 1M, but that should also include some test cases that you write for projects 1A and S and future projects. So that's what we're doing today. So ISA so far in lecture may have been just a very high level term, but in one sentence, an ISA is a set of instructions, which is why it's called an instruction set architecture. But more than just those instructions, it tells us how those instructions move around data. And in order to move around data, we have to hold different places for data. And so for LC2K, that's going to include registers. We have 8 of them, and they're going to be 32 bits in LC2K. We also have 65,536 memory locations, which are also going to be 32 bits. Which we're going to call a word in LC2K. And each of those addresses, which is different from what's in the memory location, is going to be 16 bits. A couple of the things just about where data can belong in LC2K. We have data and instructions in the same memory. So that'll be really important for Project 1S, because if you go to a dot fill, once you turn that into machine code, you can't tell if it was originally a dot fill or an instruction. But if your PC is at that location, you have to interpret it as an instruction. So that's going to possibly make some things difficult, but maybe make some other things easier. And then there is one other place where we can store data technically, and that is our PC, our program counter. Essentially a pointer, a memory address, to the instruction that we're currently executing. So LC2K can use instructions to access all the registers, memory locations, and the PC. And that's going to allow us to run any of our programs. So Sunny here is going to point out a couple peculiarities about our instructions, and we'll get into Project 1A related things.
So what we have here is like the list of all the instructions that are supported by the LC2K ISA. And so I encourage you guys to check this out in your own time. It takes a little bit of time to fully digest the capabilities and the types of instructions that you're going to use. But before we really, get into using them, I do want to talk about a couple instructions that people tend to struggle with, and talk about how they're used and how they work under the hood. The add and OR instructions are pretty straightforward instructions. They perform the different bitwise or different operations on the target registers, and they apply them to a destination register. The load and store instructions are also very similar in that they perform accesses to memory, and they can modify memory and registers based on the parameters that are passed to them. The BEQ instruction is one of the ones that I think I'm going to spend a little bit more time on right here, because I think people tend to struggle with it. So the BEQ instruction kind of means branch if equals to instruction. And so the BEQ instruction, I'm going to see if I can annotate this with a Q. BEQ instruction takes 3 parameters. The first parameter is going to be a register. I'm going to be referring to this as register A. The second parameter is going to be another register. It's also going to be referred to as register B. And the last parameter is going to be what I'm going to refer to as the offset field. So this is a really powerful instruction because it allows us to change our PC based on the values of certain certain things in registers. So branching is the practice of changing my program counter. And so if we want to branch if equals to, essentially what we're going to want to do is we're going to access the value that's stored in register A. So let's say that the value that was stored inside register A was 5. And we access the value that's stored inside register B. And let's say that's also 5. At that point, we perform a comparison operation. So LC2K only supports the quality comparison, and that's what BEQ is. And so if these values are equals to each other, then we're going to execute what's called a branch. If they're not equals to each other, so instead of both of them being 5, if one of them were 6, for example, then essentially we just do nothing. We move our program counter onto the next instruction, and we essentially perform no additional operation. However, if we are equals to, our program counter kind of will change. And the formula that you'll see that we'll use throughout this course for BEQ is that PC plus 1 plus offset is the destination. So what does that mean, right? So the program counter, to recap, is just essentially a place in memory that stores a pointer to what instruction I'm currently executing. So if my BEQ instruction was on line 5, then my program counter at that point, because we are in a word addressable architecture, will be 5 as well. But let's say that I want to change my PC to 10. Essentially, my destination, my desired destination is 10. I want to write an instruction that checks registers, A and B, and if the values inside those registers are the same, we'll change my PC to that destination. So line 10. Well, the value that goes in that third field is not going to be 10, because the third parameter is not the absolute line number, it's the relative line number. So it's where the instruction is relative to the current PC. And so if I did want to calculate it, so let's say, going back to my example, we are going to assume that our PC is 5. So we're going to 5 plus 1 plus the offset is equal to 10, which is our destination. And so we can calculate our offset by subtracting 5 plus 1 from 10. And so in this example, our offset would be 4. So one of the key things to note with branching instructions is that it is relative, right? It's not going to be, the third field is not going to be an absolute field. The other instruction that I've seen people get confused with a lot of the time is the Joller instruction. So this stands for jump and link register. So the Joller instruction takes just 2 arguments, and both of these arguments are going to be registers, right? They're going to be registers A and registers B. So prior to this, the way I like to think of this is I have this instruction also changes my program counter, similar to the branching instruction, but unlike the branching instruction, it's a non-conditional jump. So I'm not going to check for equality within any registers. I am just going to jump regardless. In addition to that, we're also going to do one thing that I'm going to get to in just a second. So the first register A stores the instruction that I'm going to try to jump to. So this is absolute, right? So if the instruction that I'm trying to jump to is on line 10, I would want to store the value 10 inside register A. So like I might do that by, for example, doing like just load 0A, and then if I had like a label that had a fill with 10 on it, that would achieve what I want. So what that first register does is it tells us where to jump to. Well, you might be thinking, well, what's really the purpose of that second register? I like to think of that second register as almost like a bookmark or you know, a breadcrumb. And so what it allows us to do is if we were to jump to an instruction, it allows us to save our spot, right? Save our old PC so that perhaps later in the program, I can come back to it. So the value that gets assigned to register B, so register B's value is going to change. We don't really care about what was in it beforehand. We're going to assign something to it. And so the value that gets assigned to register B is going to be PC plus 1. And so if my like model of execution looked like, let's say the very first line was 0 here, and then I followed it with like a joller with registers, you know, A, B, and then I had, you know, a bunch of, let's say I had a halt instruction right below the joller, and then I had a bunch of lines, and then, you know, my line 10, right? Well, what's going to happen is we're going to load the 10th line into the register A. We're going to jump to that, and we're going to save. So our PC here is 1. So the value that's going to be stored inside register B is going to be equal to 2. And so I'm going to jump to this instruction down here, and I'm going to follow them sequentially. But let's say I want to come back to the instruction that I was at. I want to come back to instruction 2, or I want to come back to the point of code that called the joller. On the flip side, I could have a joller here that instead of having register, you know, A and B, if I set my destination register to the old kind of like the bookmark register here, so I don't really care about this register here. That's just kind of, if I want to jump back to that spot, I could. But the important part is that using joller and using that second register gives me the ability to jump to a spot in code and then come back. And so that's going to be really useful in the context of functions, where you can have like code that's going to be repeated. And so you could jump to that segment of code, and then you could jump back to whatever code that called it. And so that's a very useful technique, and that reflects kind of oftentimes what happens in other ISAs. So you'll see this in like, for example, number 7 in the homework. And so that's something to consider as you're going through that. Halt and no-op instructions are fairly simple as well. Halt instructions kind of just end the program, and no-op instructions don't do anything. Awesome. Okay, let's talk about kind of focusing on project 1A. How do we represent these instructions? Because we talked about, you know, the different opcodes and the different fields that they take. But as we've discussed in class, when it comes down to it, all of our representations for code, or our ISA, are turned into machine code, which is just numbers, right? And so for LC2K, the size of each instruction that was kind of like determined beforehand is 32 bits. Each instruction is 32 bits, regardless of which opcode it is. So what matters is, where do we encode the parts of the instruction within those 32 bits that I have? So because I have 8 opcodes, I'm only going to need 3 bits to represent all 8 of those. So we talked about that last time with, you know, 2 to the 3 being equal to 8. Similarly, for both the registers, we're going to have 3 bits to represent each of those. But the other field that we didn't spend too much time talking about earlier was the offsets. So you'll note that in each of these instructions, we kind of have the 16-bit field that's changing. So sometimes, you know, like in this example right here, that's fully unused. In other cases, such as R-type instructions and I-type instructions, we are using it for different purposes. So recall that R-type instructions are add and OR instructions. And so their 3 parameters are 3 registers, right? And so that third register, what's going to be called the destination register, is just encoded at the very tail end. And so you might be asking, like, who kind of decided that this would be the way things are? So the design of an ISA is kind of an iterative process. And you'll notice that within the LC2K ISA, we have a lot of these fields that kind of say unused. Within a real, or I don't want to say real ISA, but perhaps an ISA that you would more conventionally see in perhaps your MacBook or your Windows machine or your Linux machine, it's very rare to see like fully unused bits. And the reason is because ideally I want to encode as many instructions as possible. But we're not going to focus on that. What we're going to focus on is what we have. We're trying to have a very simple ISA. And so the part that I think that people get confused about is this difference between the R-type instructions and the I-type instructions. So you'll note that for both of these examples, we are kind of reusing those last 16 bits, right? You notice that where the offset is in the I-type instruction, the destination register is in the R-type instruction. So something to consider when you're working through project 1A is the way that you treat those last 16 bits is going to be determined by the type of opcode that you write. And so those are some things to think about as you go forward. Note that like those fields are just completely unused for J-type and O-type instructions because I don't really have a third parameter, right? Or in the case of O-type instructions, I don't even have a second parameter. I just have my opcode. Cool. Anything you want to add, Mason? Are we all good?
Yeah, I think one thing about that that idea of reusing that bit field, that 16-bit bit field at the end, that'll make things really easy in Project 1S when you're essentially decoding the machine code and trying to figure out if it's a destination register for an R-type or an offset for an I-type. You can handle them the same way when it comes to Project 1S because all these bits 15 through 3 for R-type instructions right here are going to be completely zeros. So when you see unused, that means 0. So if they're all zeros, and we know that a number with a bunch of leading zeros is the same as whatever the number was, we can just treat them the same way. We could treat it almost as a 16-bit number. Absolutely. One other thing I do want to point out that's not on here, we also have our directives. And other ISAs have more directives, but in LC2K, we just have one directive, and it's a dot fill. This is not an instruction. We call it a directive because it directs the assembler to stick some value into a memory location instead of calculating it like an instruction, just literally copy paste. And that is going to be one thing that we can do in Project 1A. And beyond just numbers, we can treat this value field just like any of the offsets from the I-type instructions, specifically LW and SW. But we'll see more on what we can do with that in this next slide.
Awesome. Yeah, so let's talk a little bit more specifically about Project 1A and labels. So in those examples that I was showing you earlier, we kind of were using numbers to represent everything. But one really nice thing about LC2K is that you don't really need to calculate or count each line number. I'm sure that you'd find that annoying if I wanted to jump to X instruction, if I had to count all the lines to it and then choose that number. So what LC2K offers us is labels. Labels appear on the very left side of an instruction. And what they allow us to do is resolve what a line number is, or kind of like refer to a certain line number. And so while we do have labels in LC2K, when we are transforming the assembly language to machine code, we can't actually encode the labels as such. And so what we have to do is kind of this process of translating the labels into numbers, right? However, this makes the Project 1A implementation just marginally more difficult. And it kind of shapes the way that we have to go about encoding it. And so let's take a look at an incredibly short program that I'm just going to spin up right here. Let's say I had, an instruction add 0, 1, 2, and then I had load 0, 3. I'm going to have a label 5, and then I'm going to declare the label here. So when it's on the left side, it's the declaration. And then I'm just going to put a directive to fill the number 5 there. So that's just a very short, concise LC2K program that I just spun up. Well, if I were to just write my project 1A implementation to go, straight down the instructions in, a linear order, what you'll find is that if I look at this, I would be able to encode this successfully. But if I got to the second line, right, without looking forward, right? So at this point, I don't even know that the label or the dot fill exists, right? And I ran into the label 5, I would be very confused because I was like, I have never declared this label before. So our suggestion for perhaps how you should implement this is to kind of go about it in 2 passes. So instead of just having this one pass where I go down the code, instead we're going to go through in 2 passes. So in that first pass, we're going to do just a few simple things. So one thing we could do is you could handle errors, but I'm not going to focus on that part right now. The main purpose of that first pass is to discover where the labels are. So in this case, our label is on the second line, right? So you're going to want to kind of create some form of data structure to save these labels and save the lines that they occur at. That way, on my second pass, when I go through and I encode each of these instructions, so that first instruction doesn't have any labels, so it's still going to be a fairly simple one. But on the second one, when I run into that 5, I can reference that data structure that I generated in that first pass to discover that my label occurs at line 2. So note that for like load instructions, we use absolute labels. So the value that would be replaced with this would be 5, or sorry, would be line 2. And so I would encode that load instruction as if the 3 parameters I had received were 0, 3, and 2. Some important things to note in the process is, again, that branching instructions are relative. And so if that load instruction were perhaps instead of branching instruction, the value that would be encoded would not be a 2 and would rather be referring back to that formula I discussed earlier, relative to where that branching instruction occurred. I think so. Things to consider as you're walking through the process. Some things that I've seen that are helpful are like some students will go about implementing their first pass and then just iterate through whatever data structure they have and print out where each label occurs. And that's a good step in ensuring that like your first pass works before you even go about encoding your second pass. Some other things to consider is I highly encourage you to write your own test cases before fully relying on the autograder. If you're getting something wrong on the autograder, chances are you could, without spending too much time, think of a test case that would kind of catch your own bugs. So definitely something to consider. So that first pass, as I talked about, the output that you want to desire is essentially to generate a data structure. That second pass, we are going to print to a file, right? So the input parameters that your program receives is the name of an input file and the name of an output file. So I believe in the starter code that we provide you, we generate a file pointer. And so the function that you want to be looking at is going to be fprintf. And what that allows you to do is similar to printf that we discussed last time, is it allows you to, instead of printing to the standard cout, which is what you often see, it will print that output directly into the file. And so that's kind of the desired output that you're going to be doing in pass 2, which is you're going to be printing a singular decimal number for each instruction straight to that file pointer. It looks like you want to add something, Mason. Go ahead.
Oh yeah, this is when you're debugging your first pass, your code will look something like this, just so that you can print out essentially a map from your labels to your addresses. But going along with testing, we'll talk about testing more in the next slide. But what we don't talk about much is error checking. There's a couple, I think it's like 4 error checks that are listed in the spec. Definitely make test files for each of those. So make purposefully bad LC2K code that your assembler should exit on. Note that when it exits, you won't be able to see any of the output. So none of that will be correct. And that's because there's really no correct possible assembly file or machine code output for a bad assembly file. So there's really nothing to check correctness for besides just exiting one. But with all these errors, you can do most of them in the first pass. If you wish, you can also do some of them in the second pass. Whatever is easiest for you. But generally, the closer you have all your error checks together, the fewer edge cases you have. So if you try to do them all in pass 1, you probably won't have conflicting error checks at any point. But it's up to you ultimately.
Yeah. Let me see if I can clear out my notes. Yeah. So yeah, Mason started talking about testing a little bit. You know, you can see this calculation here. So technically speaking, we could have up to almost 6.3 million possible LC2K instructions. So we don't expect you to write 6.3 million LC2K instructions and test your program against that. What we do expect you to do is consider to test every single opcode, make sure that every opcode is encoded to what you intend it to be, as well as you consider, I think some things where people kind of struggle with is perhaps the encoding of negative values in offset fields, particularly in the branching instructions, because I believe that would probably be the only place you'd really have to represent a negative number in LC2K. Well, in addition to the .fill instructions. Well, one thing you should think about and consider is the two's complement representation. And you know, in C, or at least in our implementation of C, all integers, if you declare an integer as follows, right, is going to be a 4-byte integer, 4-byte signed integer. And so if I were to represent a value such as -5 in that integer, the most significant bit, which would be, you know, the leftmost bit, if I wrote it out in a binary representation, is going to be a 1. Consider what would happen if I were converting that to a 16-bit field. Bit masking just the last 16 bits might not be exactly what you want, and what might result in different behavior. So while you're going through writing your project 1A, and if you start running into some weird errors with regards to dealing with negative offsets for the branching instructions, I highly encourage you to think about the implications of this. And we'll go through a recap a little bit really shortly about, you know, how we switch between different two's complement representations. And hopefully that will give you some insight on that, but that's something to consider. Also, another thing to consider is different types of values for .fills. So you could have negative offsets, and we can also have negative values for perhaps our .fills. And so I'd encourage you to think about the values that would be inserted there. Some other things to consider is you should also try, so there's 2 ways to kind of use offset field for the load instructions, store instructions. the fill instructions as well as the branching instructions. And so try messing around with both having labels as well as immediate or numbers. And that should be interesting. But we don't expect you to, again, get every single possible LC2K instruction, but we do expect you to test a variety of different possibilities and a variety of different contexts. So if you're struggling with finding a bug within your code, I encourage you to go back and try to generate more test cases that might push what you would perceive to be like normal, or what you would consider an edge case or a corner case, because that's often where people fall short on this project.
Yeah, just one thing to add. I think you said something a minute ago about how negative numbers don't really make sense for like LW and SW instructions. Like it totally makes sense for BEQ that we can like branch back to a previous instruction. But still LC2K allows us to do this. So if I have a program like this, so I'll just do something, let's say that we have some sort of array, and I'll just dot fill it with a 1 for now. So we could load the address of the array, or rather, and I could do something like this, and this would have the address of the array in that memory location. So we end up loading, let's say that this is going to end up being 3. We would load 3 into register 1. Then it technically would allow us to do something like this. Oops, this should be a 1. We could do a negative offset with some sort of base that's greater. And so how this would resolve, since register 1 is currently 3, we would add that with -3 and get 0. And so at the end, the machine code, whatever this number is, I think it's like 800,000 roundabout, would be loaded into register 2. Let's put a halt there to be really certain. So that's something that we can technically do. And it doesn't really make sense because if we're thinking about C, like we would never index an array with a negative offset. That's if we're doing our pointer arithmetic, that's sort of like doing this, which doesn't really make sense. But it's something that LC2K allows us to do. And it was a specific decision to make resolving numerical offsets for LW, SW, and BEQ all the same. We could have used like unsigned numbers for LW and SW and only use signed numbers for BEQ, but it's just how the ISA is. A couple other notes on just some things to think about. So if we had multiple LWs and SWs to maybe the same location, so I'll just do array again to be simple. These two instructions would resolve to the exact same machine code, and the offset for the SW instruction would be the same as the LW. But if we have something like a BEQ, so we could have like, and this will be bad LC2K, but if we did a BEQ to start and another BEQ to start, even though these look like the exact same line, because start is in a different spot relative to each of these BEQs, they will be different. So these here are not the same, but these up here are the same. And one other thing I'd like to point out about BEQ that I forgot to earlier, I noticed how I have BEQ 00, 0. So most of the time we read the registers and do the comparison. So we could branch sometimes if we had something like this. I'll just call it target. So we might branch sometimes, we might not branch sometimes, depending on the results of that. But if our register A and register B indices are the same, whether they're 0, 1, 2, 3, 4, 5, 6, or 7, like I have in this example here, where the 0 is the same, that means we will always take that branch. There is never a case where we will not take that branch. So if you're looking for some sort of unconditional behavior, a BEQ with the same register index is the thing to look at.
Yeah, great point, Mason. All right, let's go ahead and Okay, let's go ahead and take a shot at a couple of problems. And obviously I'm not interacting with you directly, but I'm going to walk you through kind of thought process for answering each of these questions. So there's going to be a couple assumptions that I'm going to make in each of these questions, but let's go ahead and read the first one. So increasing the number of registers generally reduces the number of instructions needed to implement a C program. So, registers, the way I like to think of registers in terms of memory is they are kind of like my hands. They're very nifty. I can hold different tools in them. And when I'm holding things in my hands, I can use them. In order to use a tool, it has to be in my hands. However, in front of me, I also have my desk, right? And so let's say I have three tools here: my phone, these earbuds cases, and my pencil. I only have two hands, and so at any point I can only hold two tools. So if I were, trying to build something, and I had to use all three tools, I would have to take extra time, right? So I'd use these first two tools, and then I'd have to put, let's say, my pencil down, and then pick up my phone, and then use it. So essentially, I had to execute extra instructions to go ahead and finish the task. So registers are incredibly similar because they're very much so like my hands. So if I have more hands, right, if I can store more tools at my disposal, I don't have to worry about performing memory accesses, which is essentially what like my desk is. The process of interchanging something between my desk and my hands takes time. It's an extra instruction, usually in the form of a load or a store. And so the benefit of having extra registers is that I don't need to perform those transactions, which means that I don't need to execute as many instructions. This is kind of looking at the second question here. Increasing the number of registers reduces the number of memory accesses, loads and stores. These questions go very much so hand in hand, right? The reason that I'm executing less instructions is because I don't need to go to memory to access different variables. I already have them in my registers, and so I don't have to perform as many sort of interchanges. Now, that isn't to say that if I was running a particular program, there isn't the possibility that that one program takes the same number of instructions as the other one. But if I ever do need to, let's say I have two hands. If I only ever use one tool, well, then it's not really going to make a difference if I have two hands or three hands or four hands, right? Because I only ever need to use one of them. But if I have six tools that I do need to use, well, then I'm going to have to perform some memory accesses. So to answer, let's see if we can pull up the answers. Awesome. So to answer both of these questions, we're going to have, both of these are going to be true because I don't have to perform memory transactions. And so the overall number of instructions is going to decrease.
I think there is another question about if we increase the number of registers, are we going to reduce other instructions besides loads and stores? And so really, I think the answer is no, because you're going to be doing the exact same amount of additions. You're going to be doing the same operations on the values that you need to calculate. But there might be certain edge cases that we haven't thought about.
Yeah. So some assumptions that I'm making when I'm answering this question is that increasing the number of registers isn't going to affect other parts of the instruction. So it's not going to affect the types of operations that I can represent. It's not going to affect the range of offsets I can represent. And that's for now, that's just an assumption. What we'll discuss in just a little bit is the fact that if I were to limit the size of an instruction to, let's say I can only store my instruction as in 32 bits, right? Well, then if I wanted to increase the number of registers, well, then I would have to increase the number of bits I use to represent that and those number of registers in my instruction. And so if I want to expand all of those fields, let's say my instruction already composes all of the 32 bits. right? So in the LC2K, we talked about we had a few unused bits, but let's assume that all of our bits were used. That means we're going to have to make sacrifices in other parts of the representation so that we can fit those extra bits in. So we'll talk about that at some point. All right. So this part C asks, increasing the number of registers reduces the size of each instruction. Let's talk about this. So increasing this kind of goes back to what I was just mentioning a couple seconds ago, which is that if we were to increase the number of registers, let's think about all the implications that would have, right? So obviously there's going to be some hardware implications, but let's talk about how that affects the ISA and the representation. So in LC2K, we by default have like 8 registers. And so we represent that in 3 bits. Let's say instead of having 8 registers, let's say we had 16 registers. That would mean that we'd have to represent each register as 4 bits. And so for instructions like, let's say the add instruction where we have like add 0, 1, 2, our opcode will still compose of just 3 bits because we're not increasing the number of opcodes, but instead this will compose of 4 bits. This will also compose of 4 bits. And this last one will also compose of 4 bits. I mean, note that there's going to be unused bits in between if you recall from the representations. So the question is, does that affect the size of each instruction? No. The short answer is no. And the reason for that is, although we are modifying the number of bits that represent like each register, what we're not doing is expanding the overall structure of the instruction. Our entire instruction is still 32 bits. However, some things to consider is that, if we are limited to just 32 bits, what might end up happening if I continue to increase the number of registers? Let's say instead of 16, I had 1,024 registers. So this is a really, really big number. But then I would have to use 10 bits to represent each register. If I try to do that in this representation, well, my opcode takes 3 bits and I have to represent 3 registers, which means 3 times 10. I don't have enough space for that, right? So the short answer is that the number of registers doesn't affect the size of each instruction. In fact, if I did continue to increase the number of registers, it would eventually end up increasing the size of the instruction, because under the current representation, I don't have enough bits to the 30, it'd be 3 plus 30, which is 33. I don't have enough space. And so I'd have to increase the size of the instruction to support the increased number of registers. So that one is going to be false, because increasing the number of registers increases the number of bits per register, and in turn increases the size of the instruction. Looking at part D, it says that increasing the number of registers allows for more operands to be used in a single instruction. In short, this is false as well. And the reason for this is that if I had to increase the number of registers, let's assume, like for this case, that I am locked in at whatever size of the instruction is. Instruction size. So I cannot make my instructions bigger, right? So this kind of goes back to that example I was talking about earlier, where let's say I had 1,024 registers, which means I have to represent each register as 10 bits. Well, if I want 30 bits of my instruction to be represented by registers, well, that leaves only 2 bits to represent opcodes, right? And so essentially, the number of opcodes is now 2 to the 2, which is 4. And so I can only support 4 opcodes. And so rather increasing the number of registers and in turn increasing the number of bits that are required to represent those number of registers will eventually reduce the number of maximum possible operands. And so if I can clear this, hopefully the answer creed agrees with me. Yep. And so increasing the number of registers, again, increase the number of bits I need to represent the index of those registers, and in turn, potentially increase the size of the instruction. And on the flip side of that, increasing the number of registers could also affect the number of operands that I can represent, assuming, of course, I don't want to increase the instruction size. So why does this matter? Well, this matters within the scope of ISA design. So when we were designing, or when a professor back in the 1980s was designing the LC2K ISA, or even within like ARM, which is another ISA that we use in this class, whenever that person was designing that, they had to balance a couple of things. Often hardware and like optimization determines the maximum size of an instruction. And so it's often a balance of determining how many operations or how many opcodes you want to support, and also balancing that with how many registers that you want to have within your architecture. And so, yeah, Mason, is there anything you want to add?
Nope, that's exactly correct. And as we continue looking at the LC2K ISA, we'll see other examples of these balance act decisions that we have to make when we're designing an ISA. So now we're going to be moving into Project 1S related things. And I want to show you first this chart. We'll be looking at this chart again in 4 weeks' time when we actually get beyond simulation and actually like building hardware that runs LC2K code. But for now, since we're doing the simulator, we're going to show you some of the steps that you would take for each instruction, and then you can incorporate this into your Project 1S. So the first thing that you do for Project 1S, you have to read the instruction that you are supposed to currently execute. And that is going to be whatever is in memory at the address that is in the PC. So you read the instruction, you can store that in some sort of variable, and then you can go from there. After that, for all the instructions that deal with registers, which is everything besides no op and halt, you'll want to read your register values. And so you might store them in a separate variable. I think you can also just directly access them when you do your calculations later. But of course, after you read them, you will need to do those actual calculations. We have this thing up top called the ALU. We'll get more to that later, but that just means arithmetic and logic unit. So any sort of operators that you're going to be using in C, additions, comparisons, bitwise operators, all those are going to be used by some of add, nor, load, store, and BEQ. Then we have our memory access, which will only be with load and store. And so that's going to be indexing into a memory array. And you will have already figured out what the index is supposed to be. And then if you're not doing one of those instructions, you might still be in a BEQ or a jailer, and you will have to update the PC somehow. Now, there is one caveat with this little chart. The order for jailer of reading the register and writing the PC and writing the register is a little bit reversed. So you can look back at the spec or at the chart earlier in these slides. But what we do, we first write PC +1 to a register, and then we read the register and write PC, which is why doing something like jailer, let's see, let's just say 1, 1, we would first store PC +1 to register 1, but then we would read it again. So it does some forwarding here. And then because PC +1 is the next instruction and we are going to execute that instruction anyway, we'll just execute it. So the net effect is pretty much a no-op, except we have modified register 1 to be used in future instructions if we need to do that. But the others will follow this basic pattern. So read, instruction memory, read registers, do your operators, access memory, update the PC, and then write the registers at the end. We call that sort of a commit state at the end. But we'll get to that more later in the course, I guess. But definitely use this chart. Okay. So now we are going to go back to discussion 1 real quick, just because I think in the live sections, we didn't always have time to cover 2's complement, but it's going to be really useful for add and NOR. So we'll just breeze through this real quick. So the first thing, and this is for project 1A and for 1S, we do need to remember our bitwise operators. So we had the chart a couple slides ago of all the different bit fields and how we need to set those different bit fields to mean different things. So this is just review from discussion 1, but if we want to take a bit field, some value, and put it into an empty bit field, we first need to align it. So we would left shift it by 4, that would add 4 zeros, so that when we line it up, it looks something like this with 4 zeros at the end. And then when we do the bitwise OR operation here, it would smush them together and we would get the final thing that we want. And this works because anything that is ORed with 0 is that original thing. So this is 0, 0, 1, 0, when it's ORed with all these empty zeros, that'll be preserved. We also have a bunch of implicit leading zeros over here. So this 1, 0, 1, 0, when it's ORed with the 4 zeros, will be preserved. But when we actually do our setting of the bit field, it's reversed. So now we have zeros up top. And so the 1, 1, 0, 1 is going to be preserved in the middle. The other thing, and I guess you could not really need this for project 1A, but you could. Anything that is ORed with a 1 or true is going to be true. So if you have something that's all 1s, like a negative number that has a bunch of leading 1s because of 2's complement, which we'll see in just a second, it would overwrite everything, and that would be bad. So avoid that. You want to use zeros instead of a bunch of 1s. And then we're going to do the opposite operation in project 1S. So if we wanted to get back to this original thing here, which will be here, we would need to have a mask with a bunch of zeros and 1s. And so those are going to be placed in strategic locations. There's a couple ways to do this. We've done one way here. So if you need to chop off some rightmost bits, you can do a right shift. So this right shift by 4 would just completely eliminate those. You could also do your masking, and then we're hoping that these will be zeros at the end, and you could right shift after that, but I think technically this is going to be cleaner code. Anyway, so if you want to get rid of some bits on the right, you can right shift and it'll just delete them. But if you want to get rid of some bits on the left, you can do a mask with a bunch of leading zeros. So there's a bunch of implicit zeros before these 4 1s. And so these 4 zeros here are going to be lined up with this 1, 0, 1, 0 here. And because anything ANDed with 0 is 0, these are just going to be wiped out to 0. And then anything ANDed with 1 is preserved. So ANDing with 1 and ORing with 0 is the same thing. And so we will have these, after a right shift, of course, we'll have these 1, 1, 0, 1 lined up with our 4 1s, and then they will be preserved to our 1, 1, 0, 1 at the end. So remember that. So I know in my live section we didn't get to negative numbers, but we need some way to represent negative numbers in binary, because in discussion 1 we did some binary, and we had this idea of expanded form, how we have a bunch of positive powers of 2, but in 2's complement we're going to also use a negative power of 2 to allow us to use negative numbers. And so we're only going to have one negative power of 2, and that will be the leftmost or most significant bit. And it's going to have the strongest place value in terms of absolute value, but it will be negative. So let's see how that might work. So we have this example. Let's start off. Let's look at this number and pretend that we're not in 2's complement. Let's just pretend we're doing unsigned numbers. So we would have 2 to the power of 1 plus 2 to the power of 0, and that's 3. And look, at the end, it's going to be 3. So there are many cases where 2's complement is going to be the same as unsigned numbers. Now let's look at this next one. So let's pretend for a second that this is an unsigned number. We would have 2 cubed plus 2 squared plus 2 to the 0. So that's 1 plus 4, which is 5, plus 8, which is 13. So in unsigned, this would be 13. But when we have 2's complement, it's going to be -3. And that's because we're going to flip this bit to a negative 2 to the power of 3. So we have -8 plus 5, which is -3. And you can see this flipping here. And so notice the pattern. So before we had zeros in these first bits, and the representation between unsigned and signed was the same. But when we have this front bit as a 1, that's the only value that's going to change, and that's the only time where our values are going to be different. And because this front bit has the strongest place value, that means that any time we see a 1 at the front, that's going to be a negative number, because even if we have 1s everywhere else, it won't get large enough to overpower that other place value. So even if we have all 1s, that's actually going to come out to -1. So it will be a distinctly negative number. It won't even be 0, right? And then we also have this math trick. And to be honest, I don't know who figured this out, but this is a pretty cool idea in computer science, I think. We can get from a positive number to its negative by flipping all the bits, which means turning zeros into 1s and 1s into 0s, and then adding 1. And we'll see in, I think, a couple slides how to do some addition, but we can know that for now. Keep that in the back of your head. Right. Just a couple more things when we compare them. So here's a larger example of 8-bit numbers where we have a number that has a leading 1, but in unsigned numbers, it is 240, and in signed numbers, it is -16. So distinctly different values. However, they are related in one way. So if you take 2 to the power of the size of your number, so this is an 8-bit number, and you add that with your 2's complement representation, then you will get the unsigned representation. And that has to do with some overflow things, but that's one thing that you can do to double check if you're ever confused on converting between the two. So we did these problems last time. I'll just show them again. So this is a really, really simple algorithm that we can do. So if we have a number and we want to find its negative, we can write it out in binary, then flip the bits, and then just add 1. And so when we do this addition here, of course, if I'm adding 1, it's going to be a bunch of zeros. 1 at the end, doing our by hand addition. 1 plus 1 is 2, which is 1 0 in binary. So we have to put down a 0 and carry the 1. It'll be the same thing for a couple bits. And then finally, we have 1 plus 0, which is 1, and a bunch more 1 plus 0, which is 1. And then we get this final answer. Boom. So that is -16. Right. So once again, just for example, if we have 43 in binary, we would flip the bits and add 1, which is really simple here because we just changed this last 0 to 1, and that would give us our -43. And so I did show you, let's see here, right here. So I did the same addition algorithm that we did from the first discussion with unsigned numbers. One really cool thing is that addition in 2's complement and regular unsigned numbers is the exact same algorithm. You might sometimes have some overflow. So if you had a leading 1 over here, we're going to ignore that. But otherwise, it's going to be completely the same algorithm. So notice that this number here is is negative. So this is going to be what, like negative 15, or sorry, negative 17. And then we add 1, so that's 1, and we get negative 16. So it's going to be the exact same, right? And this is once again just showing you that we can take 2 to the power of the size of the number, add it with its negative representation, and get what its unsigned representation might be. I think there is one thing that's not on here, and that's how do we convert between small signed numbers and large signed numbers. So let's say I have this number here, which is -4. It's 4-bit signed representation right now. And let's say I want to convert it to signed 5-bit. So signed 5-bit representation. What I can do is just look at whatever the leading value is and copy that over to the new leading bits. So we see a 1 here. So the signed 5-bit representation would be just the same thing, except we add a 1 at the front. And we're going to call this sign extension. But here's why it works. So let's just kind of box off this 100 at the end. We're going to assume that that's going to have the same value because it does. But in signed 4-bit representation, this place value was -2 to the power 3, right? And now that same place value, let's see if I can extend my arrow, is going to be 2 to the power 3. But now the leading bit is going to be -2 to the power 4. The really convenient thing here is that -2 to the power 4 plus 2 to the power 3, that's -16 plus 8 is -8. So this plus this is equal to that. And that's going to be really useful for sign extension. Now note that if we have a leading 0 instead of a leading 1, sign extension is just going to be copying that 0 over. And we know that adding leading zeros for unsigned numbers or positive numbers doesn't change the value. And so that's why if we have a positive number, that means that it has to have a leading 0. If we just add a bunch of zeros at the end or at the beginning, it'll be the same number. And so I can't remember if we use that too much in this class, but we will see it in a couple of weeks, briefly mentioned in lecture. Right. So the main key here, look at the front. If it's 0, it'll be positive. If it's a 1, it'll be negative. And they do say try on your own to negate 0. So -0 is equal to 0. I think we did this last time. But -0 is going to be a bunch of zeros no matter what. So then if we turn that into a bunch of 1s, whatever size it is going to be -1. And then -1 plus 1 equals 0. Boom. So for the purposes of binary and 2's complement, 0 is going to be called a positive number. And when we get to floating point, there is going to be a positive and a -0. But that'll be something that we'll look at in a couple weeks. And I don't think we'll even mention it in discussion. Right. Going on the reverse, so if we want to take a 5-bit signed number and turn it into a 4-bit, so let me rewrite up here. And we're trying to go from there to there. We can just chop off the leading bits, whatever they are. As long as they're in the valid range of 4-bit numbers, which would be like -8 to +7. And remember that this represents -4, so that's okay. We can just chop off the leading ones. And so you might do that with a mask. I remember a couple slides ago, we changed a bunch of things to 0. We chopped them off by doing a mask with a bunch of zeros followed by a bunch of 1s. And so you'll need to do that in Project 1A for sure, if you ever put a negative number into an offset field. So think how you might do that. All right. And then finally, your computer is going to do a lot of this stuff automatically. So things like converting from larger numbers to smaller numbers, it might not do that automatically unless you know your built-in types really, really well. But most of the time, it's going to do all the operations automatically. So addition, subtraction, all that stuff, your computer will do it for you, and it's always going to store it in binary. So if you ever see a decimal number, it's actually binary. If you ever see a hex number, It's actually binary. It just prints it out on our screen. It's nice and easy for us. So if you ever need to manipulate individual bits, just do it within the number. Don't make an array of zeros and ones, because that gets really, really messy really, really quickly. You have to do a whole bunch of multiplication, and I do not recommend it. Okay, so that's the quick review on two's complement and the bitwise stuff. And I do that because we're going to look at how we might do that in LC2K and what that means for LC2K. So first we have this add instruction, and I'm going to mention this briefly because it'll come up a lot in Project 1M. But we have this add instruction, and the add instruction is useful, not just if we can add things, which is obviously useful, but that also allows us to do some basic multiplication or left shifting. So if we add a number to itself, that's obviously the same as multiplying times 2, which is the same as left shifting by 1. So obviously, if we take the result and then add that to itself, do that again and again and again, we can left shift by any arbitrary number. And we might have to do that in a loop, which we will do for Project 1M, but that's something that we can do. And so we get this bottom true statement. So if we do it multiple times, then we can left shift it by some arbitrary amount. And don't forget about overflow. And then we also have this other instruction in LC2K, and I get a lot of questions. Why NOR? Because it can be really confusing to think in terms of NOR operations. But in LC2K, because we wanted to make it as simple as possible, we wanted to keep ourselves to 8 instructions. We're going to use this NOR because it is what's called a universal gate. So if we want to do some regular OR operations, then we would need to implement either a NOT or maybe an AND or something else in order to get the full range of logical operations. So just a couple examples. If we want to actually do the NOT, a bitwise NOT, we can just NOR something with itself. And that's because when you OR something with itself, it's that same thing. So you do the OR and then you NOT that, and you get the NOT of the original thing. We can also do a NOR, or rather an OR, by first doing the NOR and then taking that result and NORing it with itself. So using the definition of NOR and this idea that we can get to a bitwise NOT by doing a NOR with itself, we can do the same thing to get an OR. And then we do have to use some review from 203 or 270, De Morgan's laws, in order to get to an AND operation. So if we take a value and we NOT both of the inputs first, so that is doing a NOR with itself on both of the inputs, then we can NOR those two results together. And by De Morgan's laws, this bitwise NOT distributes, cancels that, but turns this into an AND. And so that's going to be really, really useful for Project 1M, because we will need to do some masking in Project 1M. So that turns into an AND. And you can look up more on Wikipedia. There's ways to do XOR, XNOR. I guess if you took this AND operation and did a NOT, you could get a NAND. But that'll be really useful for Project 1M. Okay. So I say all this because what if we want to do subtraction in LC2K? Now ARM has a dedicated subtraction, but if we want to do subtraction in LC2K, all that we have to do is first do a NOR with itself on the second operand to get not B, I suppose. Then if we add 1, we get negative B. And then if we add the negative B plus A, we get A minus B. So we can do subtraction in LC2K with 3 instructions instead of 1, but that's okay. And you might even need a 4th to load this positive 1 here. So I'll just mark that as an LW. And then finally, we can do a bunch of adds to do our left shifts, and then 3 NOR operations to do an AND operation. And that gets us a total of masking. Similarly, if we want to set some bit fields, we can do some left shifts and then do 2 OR operations, or NOR operations to get 1 OR operation. So there's a lot of variability there. Right. Now I'm going to turn back to Sunny, and we're going to go through some of what I call brace blocks in LC2K and how we would translate that into LC2K from C. And that'll be really useful for Project 1M.
Yeah. So I'm sure that you guys in your computer science backgrounds and careers so far have seen a whole lot of code that kind of looks like what we have off to the left here. So this is an example of some code in C. What I don't expect you to have as much experience with is writing code that would be the equivalent to this in an assembly language. So what we're going to do here is we're going to try to translate what we have on the left, which is kind of like this if else statement, into what we have on the right. And so I'm going to walk you guys through kind of my thought process and also kind of identify some key characteristics of this block. So I'm going to try my best to kind of color code this and kind of identify what parts of code are being encoded in each one of these. So looking at this if else statement, we essentially really have like 4 segments of code. So the first segment is what I'm going to mark here or underline here in red, which is the condition, right? So this is right now, we're going to compare the values that are stored in registers 2 and registers 3. And based on the whether that returns a true or a false value, or a 0 or non-zero value, we're going to change the code that we execute, right? So the second part of code that I'm going to underline here in green is the code that is executed if the statement is true. So this code is only going to execute if the value inside register 2 is not equal to the value inside register 3. The third component that I'm going to underline here in yellow is the code that is in the else block, which is a code that executes if the value in the statement resolves to false. And the last part of code that we have, it's not really code right now, but that we could have is whatever code occurs at the very, very bottom, whatever code that executes after, the if else statement is done. So that code is going to be executed no matter what, regardless of what the condition is. So let's take a look at how we could perhaps do this in LC2K. So recall the one instruction that does comparison for us and allows us to branch based on that is the BEQ instruction. Right here in our condition in this case, we are trying to compare whether register 2 is not equal to register 3. So we only have an instruction that compares that if they are equal to each other, right? And if they're equal to each other, we're going to perform some sort of jump. So the values that we're going to have as parameters for this part are going to be registers 2 and 3, because those are the registers that we want to compare, right? These are the registers that are going to appear in the condition. The destination, so here we have a label. I'm sure you could put a number as well, but for sake of simplification, we've included a label. So this is the part of the code that is going to be jumped to if this condition evaluates to true. So essentially, if this condition evaluates to true, we want to execute this bit of code right here. We want to execute that green code, right? Well, currently the way we have our code structured, we are going to jump to this else branch if we evaluate, if this statement evaluates to true, if they're equals to each other. And so the code that we would kind of want to occur here, because we are checking for non-equality, right? So if these are not equals to each other, recall, then the code that we want, essentially, if this evaluates to true, which means that they are equals to each other, the code that we want to execute is right here, this yellow code. And so the code that we're going to put at the else kind of block here is going to be correlate to the yellow segment here. On the other end, right, if that BQ23, right, if register 2 is not equal to register 3, we want to execute the green code. So if a BQ instruction does not, is provided registers whose values are not equal to each other, or that are not equal to each other, then the code that's going to execute is just the line after it, right? Essentially, no operation, no branching operation is performed. And so the operation that's going to execute is right here. However, if we just had these statements, so if we kind of ignored this statement right here, this third line, what would end up happening is that we would end up executing both instructions, right? So ideally, we execute our green code, and then the next code that we execute is going to be the blue code, right? The code at the very bottom, any code that occurs after the condition. So our blue code kind of exists here. So in this case, we don't execute anything after, so we have a halt here. But if you wanted to perhaps execute an add instruction or any sort of other instruction there, you could also have that there. So the reason we have this statement right here is so that we don't execute the yellow code after we finish running the green code. So this is the overall structure of an if else block. We have a condition that we will generally check using a BEQ instruction. So note that it's kind of inverted because we can only check for equality. We don't really have B NEQ. We only have B equals. And so if that evaluates to true, we are going to execute the code that should be associated with the label. So in this case, the label is else. The code that should be executed in association with else is the code that should be that should execute if they are equals to each other. So in this case, we want to execute R1 is equal to 0 if R2 is equal to R3. So that's why we have that on this line. The code that executes when they're not equals to each other is in this case the green code. And so this is going to be like the overall structure of any if else statement. And so you'll find this extremely useful, perhaps in, as Mason mentioned, Project 1M, but also even more generally is as we move forward in projects 2. But yeah, so this is an example of an if else statement. We're also going to look at a couple other types of common statements that you might see within C. Cool. Mason, could you just hit the next button? I don't know why it's not letting me move my slide forward. Okay, cool. It's good. All right, so the while statement is also another example. So what a while statement essentially does is it keeps running the code. So in this case, the blue code inside here until the condition in the red text it evaluates to true. So in this condition, in this example, we are looking at, we are trying to run the code until R2 is, as long as R2 is equal to R3. Essentially, we want to only jump. We only want to, if we had like, if we can use the same colors. If we had code like after this, right? I'm underlining this in green, right? We only want to execute that green code. We only want to jump to that green code once the condition evaluates to false. So essentially, what we can do here with the branching instruction is we can compare the values inside registers 2 and 3, and only when they're equal to each other, we will jump to the code, to the green code, right? So we'll jump down to this part. However, what In the middle here, we're going to have, so if that condition does not evaluate to true, we will then continue to execute the next line, which is found here. So this is kind of the literal translation of that. The last line that we have here, so recall Mason mentioned this earlier. If we ever have a BEQ instruction where both of the registers provided are the same, then obviously the values inside those registers are going to be the same. And so essentially, what we are going to do is, regardless of what values in register 0, we are going to change our PC. We're going to jump all the way back to this line over here. And so essentially, the form of execution that we're going to see is we're going to check a condition. We're going to execute whatever lines are inside that loop. So here I've illustrated that as the blue code, where we're adding one, add 111. And then at the very end of that, we're going to jump back to the start where we're checking the condition. And so essentially, we're just going to be checking a condition over and over until we can kind of break out of that condition. So in this case, in this particular program, we're going to kind of be stuck in an infinite loop because we're not R2, unless, sorry, if R2 is initially different than, R2 is initially not equal to R3, then we're going to we're never changing R2 or R3. So we're going to kind of end up in an infinite loop. But more generally, you could modify, for instance, registers 2 or 3. And so you could keep iterating through this code until that they meet certain values that you want. Awesome.
There's something I want to mention.
Yeah, go ahead.
There's one example that we don't have in the slides, and you may have used this in C or C++, but we do have one more type of block called the do while. So a do while block is guaranteed to execute whatever's inside the braces at least one time. So it'll execute it once, guaranteed, and then at the end, it'll check our conditions. And if this is actually much easier to translate to LC2K. So it would look something like this. So we could add a label do which is the beginning of our brace. We could do our same add 111, and then we would do our BEQ. Let's see, 2, 3, and actually I'm going to modify something here.
I'm gonna make it equals equals.
Yeah. So and the reason I do that is because when we have a do while loop, when we do our condition checking at the end, we actually can check for equality. So if you're truly trying to check for equality in a while loop instead of inequality, you can do something like this. The only caveat is that it will happen at least once. I suppose at the beginning, if you really want to do a true while loop, you could add an unconditional branch to the, maybe we could do something like this. So you could branch to the end first, then do your condition check, and then go and do the thing until that condition breaks. But that would eliminate the need to have, I guess, other unconditional branches that always execute. It would also eliminate the need to have some sort of end to label that is after the end of our loop here. But so you might want to use that.
Yeah. So like what we're showing in this, what we're hoping to accomplish is show you a couple ways of doing it. I'm not, the ways that I'm showing you are not holistic. We're not showing you every potential way to represent a while loop in LC2K, but this is just a very common way of doing so. So Mason here illustrated another way to do a while loop, and he also showed us how to do a do while loop. So yeah. So another type of common convention that you might want to implement in LC2K is a for loop. So breaking down exactly what a for loop does, there's really 3 parts of it. In fact, they're actually quite similar to while loops, but the difference lies in the top part, where we declare what we initialize a certain register or variable to a starting value. We have a condition, right, really similar to our while loop that we are going to constantly check, and we're also going to have a certain operation that we're going to perform every time we perform this loop. So in the case of the example here, we initialize register 2 to 5. So that's only going to execute once when we initially run this loop. The very first time we're about to run this loop. The second part is going to be that condition. And the second part in red is going to be that condition, which we're going to check every time we run the loop. And then the third part is going to be what I call kind of the iteration step, where we're going to modify a variable. And that's going to occur at the end of each loop iteration. So the composition of this kind of goes as follows. So when we're trying to initialize something to a certain value, so in this example, we are trying to initialize register 2 to 5. So we could do this using a load instruction. So second. Is it going to let me write? Oh. Second. iPad, respond to me, please. Okay, cool. All right, so my iPad's not listening to me, so I'll just verbally explain this part. Mason, you can take any notes that you see fit as we walk through this. So that green part at the very top there is us loading the value 5 into register 2. So note that in this example here, we don't actually show you the label 5, but presumably at the end of our program, we'd have something that would be labeled 5 and have like a dot fill 5. And so we don't show that right now. It looks like Mason's drawing that for us now, but essentially what that accomplishes is we're initializing a register to a particular value. So that line of code is only going to be executed once. The second thing that we might do is we have what is considered like our condition. So that's what's in red. So that's what you see on the third line. So that's going to be very similar to what you saw back when we did the while loop. So we're going to check that condition every time we iterate. The third part is going to be what's located inside the loop. So that's what's in blue. So we're performing the operation add 1, 1, 1. So this is what's new, is everything in pink. This is kind of the main difference between a while loop and a for loop, is that we want to kind of perform this increment operation every time we execute the loop. So this is going to be the last thing that's going to happen in the loop before we branch back to the start of the for loop. And so we want to, our increment operation here says plus plus R2. So essentially we want to add 1 to the value of R2. Well, in order to do this, we have to first have the ability to work with the number 1, right? And so you can see at the very start of the for loop in the second line here, we load the value 1 into register 5. Therefore, by doing that, in the fifth line, by performing add 252, essentially we're taking whatever values in register 2, we're adding 1 to it, and we're storing that back in register 2. Then we go back to the start of our loop. So essentially, what this allows us to do is change the registers and change the values of the registers that are in our loop condition. So like last time in our while loop, we saw that we were never really changing registers 2 or 3. And so we would kind of end up getting stuck in an infinite loop. However, here in this for loop, we are modifying register 2. And so essentially we're going to add 1 to register 2 until we have a value where register 2 is equal to register 3. And then we're going to branch all the way to the end of the instructions with the end label.
Yeah, a couple things I'd like to note. So just like we had with the while loop and the do while loop in the last slide, we could construct this a different way. So let's see. So assuming that this top part is going to be the same and that bottom part is probably going to be the same. So we could have some way to branch to the end. So let's, or maybe we'll call it check, like we did on the last line. Then we have whatever stuff we're doing inside the for loop. So that's add 1, 1, 1. Oops. And then of course we increment. Do increment. And then we have our check condition, right? And that here is BEQ 2, 3, 4. And of course, this would have to be if our for loop was checking R2 being equal to R3, but we could do it this way. Also, we'll get more into this later in the course on compiler optimizations, but sometimes compilers will be able to tell if the condition is true on the first iteration of the loop. And if the condition is guaranteed to be true on the first iteration of the loop, then we never have to do this. So we might not need this. We might not need this if the condition is guaranteed to be true at the beginning. So I'll call it at the start. And so if you are doing something again for project 1M, where you'll probably have to use a loop, you might have some sort of structure that looks like this. So you do your stuff, you do your increment, then you do your check, which branches backwards. So keep that.
Just a quick clarification. It would be when it's not true, when they are, if it's never gonna run, in the sense that if the condition always evaluates to false, right?
Let's see. So let me think about this again. So if the condition starts off as false, we would go down here and check. Then 2 would be not equal to 3, and so we would continue along our way. So it would guarantee that the condition is true. Of course, if we're checking R2 being equal to R3. So yeah. So you definitely do have to go through and make sure that all your conditions are correct, because if you're doing something like a do while loop, it'll look like the correct condition just at the end. But if you're doing a regular for while loop, you might do it inverted. So
yeah,
you just have
I don't think, yeah, just a heads up. I don't think we don't talk very much in this class about compiler optimization. So of course, this class is an introduction to compilers, just so everybody gets a good idea of how they work. However, I believe in, I may be wrong, but I believe it was homework 2. Historically, we've offered like a question which kind of encourages you to check out some other compilers that run on C code and take a look at what optimizations they make. And that was entirely optional, I believe. But if you're interested in compiler optimizations, I encourage you to attempt that question on that homework if we end up having it.
Yep. All right. So now we have a practice problem. And so let's then go over the solution. But one thing to keep in mind, this practice problem has 2 parts that kind of cover everything that we've done in the past couple minutes. So first, there's an arithmetic operation. So we have to do that calculation. And then we will translate the if-else block.
Yeah. All right, let's take a shot at it. So at the very top here, I'm just gonna a second. Let me see. Oh, I'm on my eraser. Okay. So I'm gonna save some. Okay. I'm gonna save some room just for some loads. So I'm gonna assume initially that I have all the variables I have on hand, and I'm just gonna declare some loads as I go. So let's start I generally like to start where the code essentially happens. So I'm going to designate. So it looks like I have unsigned val. This is going to be a variable, right? And so I'm going to choose some register to save this variable in. Let's see, I want to kind of stay in line with the answers. So let me check really quickly where we put that. Mason, do you know off the top of your head?
Let's say register 2.
Yeah, sure, that works. So we're going to store val in R2. Here we have another variable. It's an integer, and this is going to be a signed integer, and we're going to store that in, let's say, register 3.
Let's say register 1.
Okay, cool.
And we'll see why in just a minute here.
Awesome. All right. So we're going to store those variables in those designated registers. So if you're trying to turn some C code into LC2K or really any assembly, one of the first parts is kind of deciding what registers are going to, or what variables are going to be stored in what registers. And so that's what we've done here. So none of these variables are kind of initialized to any value. So we can just assume that we're not going to load anything into them initially. Okay, so here we have an if block. And so in that if condition, we take the modulo 8, and then we take the result of that operation, we compare it to 0. So perhaps the first operation we really need to do is get the value modulo 8. So let's think about what modulo 8 is actually doing. So what the modulo operator does is it kind of takes, it's essentially a remainder operation. It gets the remainder of the value when divided by 8. So if I had the value 9, the resulting value that I would get would be 1, right? And so let's think about, or similarly, if I had like value 8, the remainder would be 0. So let's think about how we could possibly perform this operation within using bitwise operators, right? And what we're going to use is we're going to use bit masking. So let's look at like the representation of those two examples I gave you, where we have the number 9, right? So I'm going to represent 9 as follows. So 9 can be represented as a 1, 0, 0, 1, right? And let's look at the representation of the number 8. So this is going to be 1, 0, 0, 0. Let's find a couple more examples. Let's think about the number 16, right? That's also a multiple of 8. And so we would expect the modulo operator to give us a remainder of 0, right? And so let's look at the representation of 16. So that's going to look like 1, 1, 0, 0, 0. Well, how about one last example of a value? Oh, sorry. Yeah, that's correct. It's 1, 0, 0, 0, 0. And then let's look at one more value, like perhaps the number 11, right? So this is going to look like 1, 0, 1, 1, right? So both of these numbers, 8 and 16, are numbers that kind of satisfy my condition. And if you look at them, and I encourage you to perhaps try numbers like 24 and 32, other multiples of 8, you'll notice that all multiples of 8 have their last 3 bits set to 0. And why does this make sense? Well, those last 3 bits are going to be 0 because those last 3 bits represent non-multiples of 2 between the range 0 and 7. Any value to the left of that, any ones that I have in the binary representation that I have to the left of that are going to represent values that are multiples that are going to have 8 as a factor, right? They're going to be multiples of 8. And so what determines whether something is a factor, is going to have a modulo of 8 that's equal to 0 or not, is going to be these last 3 bits. So essentially, we want to check if these last 3 bits are equal to 0 or if they're not going to be equal to 0. Well, let's think about what operators we learned that we can use to isolate these 3 bits and then compare them to like perhaps the value 0. So I'm going to erase some of this really quickly. Cool. That should be good enough. So let's go ahead and write some LC2K. So what we want to do is we want to isolate those last 3 bits. So if we were writing C code, for instance, well, what we might want to do is we might want to perform a bit mask. So so right now our val is stored in R2, and we essentially want to say R2 is equal to R2, not R squared, R2, bitwise ANDed with 0B111. What that does is essentially isolates those last 3 bits. Then what we might want to do is we might want to check essentially if once we perform that operation, if that is equal to 0, right? Because if that is equal to 0, that must mean that our val, or the value that's stored in register 2, is a multiple of 8. So let's go ahead and write some and think about how we could perform a bitwise AND. So you might notice off the bat that we don't have a AND operator, right? We're limited as far as like R type instructions go. We're limited to add instructions and NOR instructions. So this kind of goes back to what Mason was mentioning earlier, where we can use the AND instruction or use the NOR instruction to construct other logical gates, such as the AND gate. So the way we do that is we perform. So if I wanted to, and I'm just going to kind of recap this. If I wanted to perform the bitwise AND between registers A and B, right, I would perform a NOR on A with A. I would let's just reassign that to, that'll give us not A. I could perform the same operation on B, and I could produce A and B by performing the NOR on the results of both of those operations. So let's go ahead and write that in LC2K. Well, to start, I need to load this value into a certain spot in memory, right? So let's just load that into perhaps register 3. Is that a good one, Mason?
Yeah.
Okay, so let's load that into register 3. So what is this value? Well, in decimal, that's going to be 7, right? So I'm going to load into register 3 the value 7. Right. For now, whenever I write a number like this, I'm going to assume that at the bottom there's going to be a label that says 7.fill and then the actual integer, right? And I'll do that at the end. So what we want to do is take R2 and perform a bitwise NOR with itself. So let's go ahead and do that. So we're going to go NOR. We're going to do register 2 with register 2. And we can probably just save that inside register 2 as well. So essentially what we're doing here is we are flipping we're performing a bitwise NOR on register 2 and saving it back to register 2. We're probably going to want to do the exact same thing as we illustrated at the bottom here for register B. And so we're going to do the same thing for register 3. So now I have gotten these two values. Well, now I'm going to perform one last bitwise NOR, which will give us the result of A and B. And so let's just save this to, I guess, just register 3, because I don't think we're going to need the value 7 anymore. So what we're going to do is we're going to form NOR 2, 3, and then we're going to save it to register 3. So essentially what we've succeeded in doing here is we've performed this operation here, and we've saved the result of that operation in register 3. So we've successfully made a bitwise AND in LC2K. So now we want to see if the value in that register is 0. So this is going to come back to like a common convention that I highly suggest that you use in LC2K. This is simply a suggestion, which is you're going to need the value 0 a lot. And every register in LC2K is initialized to 0. And so usually it's good practice to just maintain the value of 0 inside the register 0. So I'm going to take advantage of that at this point. So I want to compare, and I want to check if the value inside register 3 is 0. So the way I do that is I do a BQ, a comparison of equality, between register 0, which has the value 3, has the value 0, and 3, right? Which is going to have the result of val modulo 8. And if it's true, I'm going to jump to a certain label. I'm not going to define this yet. So let me go ahead and erase some of my work, so we have more room to write the rest of the LC2K code. Awesome. Okay, so now let me switch colors really quick. So now we've successfully done the operation inside the condition, and going back to what we were talking about earlier with if blocks, right? If this condition evaluates to true, right, which is essentially what we're checking here, I want to execute result is equal to 1. So the value that I'm going to, or the code that I want to execute when the branch instruction is executed, is result is equal to 1. So I'm going to write my label all the way down here called true, and what I want to execute is result is equal to 1. Well, initially I said that result is associated with register 1. And so I can load the value 1 into register 1. So here the destination register is register 1, and the value that's being loaded is as follows. However, on the flip side, if that if statement evaluates to false, then I want to assign the value 0 to the result. And so I could, one way of doing that, there's actually several ways of setting a certain register to 0, but the way I'm going to do that is performing an add instruction. So the red code is here. So I'm going to perform an add instruction, and I want to save that to register 1. So I could do add 0, 0, 1. And the reason this sets register 1 to the value 0 is because the register 0 we're going to maintain has the value zeros. And so 0 plus 0 is equal to 0. However, going back to what we were talking about earlier, we don't want to execute result is equal to 1 if we hit the done condition. So we might call this I'm going to check the answers really quick. Okay, so we have a label called return in the answer solution. So I will maintain that. So if I have return here, so return is essentially whatever code falls below this, the segment that I've shown. So because there's no code there, I'm just going to call it a halt instruction for now. Right. So what I want to do is I want to jump down to my return label. Well, if I want to jump there no matter what, as long as I set these registers equal to each other, so just out of common practice, I'm going to use 0, 0. And the destination that I want to jump to is the return label. So it's like I'm going to erase these random ends. So let's really quickly now. So I referred to the number 7. I referred to the number 7 earlier, and I referred to the number 1, and I referred, well, I guess that's the only things that I referred to, but I referred to these numbers. So at the very bottom, I'm going to have a couple dot fills that defines them, right? So I might have 7 dot fill 7 and 1. Blue is probably not the best color for that part. 1 dot fill 1, and yeah, I believe this should be correct. So Mason, do you want to reveal the solution real quick? Oh, there it goes. Awesome. So let me check. So here in this example, you'll note that there's a couple extra instructions, and that's just us, providing example inputs for what val and result, or sorry, what val is like initialized to. So here we say that like val was initialized to 16, but that could really take any particular value.
Yeah, awesome. One thing I do want to point out, and I think I may have mentioned this in discussion 1, but this will be really important for project 4, not 2, project 4. When we did the modulus with 8, we got 7. And that can be generalized to any power of 2. So we have some value, modulus a power of 2. That's going to be equal to that value ANDed with that power minus 1. So 7 is 8 minus 1. And here's why if we draw 8 in binary, it's this. And so we have 3 zeros at the end. We want to preserve those 3 zeros, right? And so we just subtract 1, and that'll turn this into 0 and all these into 1s. So that's why we do that. And that's equal to 7. Right? So yeah, not particularly relevant for LC2K right now, but that'll be really useful later on in the course. So let's keep going, I guess. This is the starter code from the Project 1 spec. And we do get a lot of questions on what exactly this is doing. So I want to go through real quick and convert it into C code. All right, so let's look here. So a couple things I'm going to notice from the beginning. I have a couple constants. That's constant. That's constant. I'm loading that constant there. And let's see. Oh, and this is tricky. I'm loading the other constant, -1, somewhere else. But we'll figure out how to do that in a minute. A couple other things, and of course I give you the comments here that it decrements. But if I see some sort of add where one of the source operands is the same as the destination operand, that's similar to like a plus equals in C++. And then finally I have a condition check with 0. And then I have an unconditional branch, like we were talking about earlier. So if I see an unconditional branch that goes backwards, I'm thinking it's a loop of some sort. So let's look at this. So first thing we'll do, we'll put 5 into register 1. I'll just, let's see, I'll have an int register 5. I'll set it equal to, or sorry, register 1. I'll set it equal to 5. And that looks like an 8, unfortunately. Anyway, so I'll set register 1 to 5. And then I'll also have to use that value in order to figure out what our next LW is doing. So register 1 is 5, and my color changed again. There we are. Now we have 1 in register 5, or sorry, 5 in register 1, and we're going to read register 1 on this next line. So if you remember, the LW instruction takes the value in register A plus the offset, and then calculates that as our memory location. So 5, which is in register 1, plus 3 is 8. And then we do have to do some counting. So 0, 1, 2, 3, 4, 5, 6, 7, 8 will get us to -1. So now, enter register 2, let's call it, is equal to -1. Okay. Then I see that I'm going to be decrementing register 2. Since this is -1, that plus equal is essentially something like this, right? And then I have a BEQ. So when register 1 is 0, then I'll go to here. So 2, we're going to go to PC plus 1 plus 2, which is this halt. So this BEQ points to the halt. So I'm doing some sort of jump to halt, and then I have my loop. So let's see. So at the very first iteration of the loop, it's going to decrement. And so register 1 is going to start off as 5 and then get decremented to 4. And then, of course, 3 and 2 and 1. And then finally, once it's 0, it'll go to the end. So essentially what this is doing, let's say I said that that would decrement from 5 down to 0. So that's going to happen 5 times. So we know that this loop is going to occur 5 times. And so we can write it as something like this. We could do like while that. And then that would actually be it. But to make it easier to read, I do have a solution that's probably more like what we would actually write in C available for you. So oftentimes we don't use absolute register indices when we're writing in C code. We have our favorite variable like X or I or J or something. So we could have X start off as 5 and then we decrement it every time. We could also do this in a for loop. And like I said previously, we could also do something like while X minus minus, and I think that might actually be a minus minus X that we have to do. No, that's completely right. So you could just generalize it to one line, which is pretty cool. You would still need to initialize X though. So there's multiple ways to translate into C, but the goal is to get closer to whatever you would actually write when you're writing C code. And so I think probably the best way here is to do it with the for loop. And this needs a semicolon because we use for loops a lot. And when we look at the for loop here, we can identify those 4 colored parts that we had a couple slides ago. So we have our initialization here in it. We have our condition check, which is here. So there's our check, init, check. And then we have no actual body stuff, but we do have our decrement, which is here. So those are the 3 parts of the for loop. And that's why it's probably best to turn this into a for loop. Right. So that's that problem. Real quick, before we end here, we're going to go over the algorithm for Project 1M. And in order to understand the algorithm for Project 1M, we do have to look at expanded form. So when we do multiplication, we can do it similar to expanded form. So we break everything into its parts, its place values, its digits. We do all the multiplications, and then we add together the final sum. And so that's what we're going to be doing here. So just looking specifically at the binary, when we do the multiplication here, either we include the number if it's a 1, or we exclude it if it's not there, or if it's a 0. So we're going to use that idea quite a bit. So when we do regular multiplication with decimal numbers, this is something that we learned in grade school, but it'll go something like this. So we'll pick one number that we're going to go digit by, and I'm going to pick this bottom one. So we have 26 times 104. And what we do, we take the top number, multiply it by the first digit, and then we store that result on a first line almost. Then we're going to add a 0 because the 2 has a place value of 10. So that's added 0. So we'll go ahead and write our 0 here. And then we'll do the same thing. So we'll take 104 times 2, which is 208. And we'll place that to the left of our added 0. Then we'll add it all up and we'll get our final answer. And so you can verify that 104 times 26 is equal to 2,704. Just like addition, the algorithm for multiplication in binary is going to be the exact same. And if you're looking for more clarification, you can find it, I believe, in section 3.3 of the textbook. Unfortunately, we don't provide the textbook. We can't do that due to copyright. We don't want to be like other schools that have provided it online for free publicly, because that would be very bad. So let's look at the actual algorithm here. So we're going to pick a number that we're going to go bit by bit for. I'm still going to do the bottom number, but you could totally do the top number. And so I'm going to start off with the first one. It's a 1. And so I'm going to take 1001 times 1. It's 1001, so I'll just copy it down. and then I'll add a leading 0. And remember, in LC2K, to add a leading 0, all you have to do is shift by 1, which is adding it with itself. So at this point, we would take 1001 and add it with itself, store it in some other register, and then we can keep going. So now looking at the second bit, it's a 1. 1001 times 1 is 1001. So we'll just copy it down, right? Now we encounter a 0, and anything times 0 is 0, so it's just a bunch of zeros. And then finally, same thing, 1001 times 1. We've now shifted over 3 times, so we have 3 ending zeros. And then once again, 1001. So now we add that all together in some sort of running sum, and we get our final answer. And you can verify, let's see, this is 9 times 11. So we're expecting that this should be 99. And I haven't done the math myself, so let's see, this is 32, I believe, plus 64. That sums up to, what, 96? And this over here is going to be 3. So it does sum up to 99, which is nice. For Project 1M, we have a couple difficulties. We do have to figure out how to isolate the individual bits to see if they're 1 or 0. And so to do that, we can do the masking stuff that we did earlier. We showed you how to do an AND operation in LC2K. And so you can do that with some sort of mask, and that mask will have a single 1, and all the rest will be zeros. You'll do the AND operation between that mask and the number that you're going bit by bit for, and the result will either be 0 or will be something else. Don't worry about right shifting, because if it's a 0, you know that bit was a 0. If it's a big number or 1, you know it's a 1. And so you can use a BEQ with 0 to tell you if you should add that shifted number to your running sum or not. So here, we would probably just skip over whatever addition. So skip addition if we were able to BEQ with 0 and whatever the result of our mask was. Otherwise, we would do the addition with this shifted number. And if we have some other register, let's call it register 7, that's our sum, we could keep adding this into our register 7 sum over time. And at the end, we would have the correct answer. A couple of notes about Project 1M, by the way. We're only dealing with 15-bit numbers. So here we're doing a 4-bit example, but you would have to do it with 15-bit numbers. The reason we do that is because if we were to do 16-bit numbers, that would require 32 bits maximum for a product. But since we're doing 2's complement for all of our words and registers in LC2K, if we were to multiply 16-bit numbers, it could overflow, turn something negative, and we don't want to do that. So we're only going to do 15-bit numbers, right? And that is the algorithm for binary multiplication. There are ways to do this quicker in hardware, but again, LC2K is a very simple ISA. We only have the add instruction. We don't have a multiplication instruction like ARM or x86 or something. So we have to do this manually instead. A couple things for Project 1M and your test cases and Project 2C, which is also writing in LC2K assembly. You might want to write it in C and then use the things that we've taught you today to translate it into LC2K. Also, it's always good to add comments. You'll notice that everything that we provide to you for LC2K is going to be very well commented, and it should really be the same so that you can understand your own code and so that we can understand it in office hours. This has been discussion 2